Welcome to E-Pathsala lecture series on computer science. We are discussing about the paper Cryptography and Network Security. In this session, we are going to discuss about modular exponentiation. To review the concepts of modular exponentiation, to find the purpose of modular exponentiation in cryptography, and also we are going to discuss about the inverse multiplication and some of the examples related with the modular exponentiation and the inverse multiplication. Keywords are modular exponentiation, inverse multiplication, Euclidean algorithm. The last session where we introduced about the modular polynomial arithmetic, in that we have taken the g f of 2 power n, that is the field where we do the computation to form a field, and also can able to always to find a inverse with the help of Euclidean's inverse algorithm. So this is an example where we are taken in the last session. Now when I am going to use this, so here, so polynomial arithmetic modulo, we can able to see that x cube plus x plus 1, that is when I am taking gf of Galois field of 2 power 3, I am taking x cube plus x plus 1 is nothing but irreducible polynomial. What is an irreducible polynomial? A polynomial, it has no divisor except itself and 1. So now this is going to be playing a important role in performing the modulo operation. So as we know, the field has two operations, addition and multiplication. So we can able to see that addition and multiplication table, which is explaining about here, as we are taking g f of 2 power 3, g f of 2 power 3 means we will take 3 bits 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1, that is 3 bits, that is 2 power 3 bits, and these 3 bits are going to be represented by, if I have all 0, I can say that is 0, if it is 1 1, next, that is this is your x, where the when you are going to represent this binary in terms of your polynomial, we say that 1 x plus x square, that is the meaning. For example, if you take all the coefficients are 1, I can represent a term here. You can able to see that x square x plus 1, how we represent in the polynomial. Now we take 0 1 0, it is x, 1 1 means x plus 1, 1 0 0 means x square, 1 0 1 means x square plus 1, 1 1 0 means that is your, the x square term is 1, xth term is 1, that 1th term is 0. So we are not using that x square plus x. Then 1 1 1 means all the terms are there in the polynomial. We say that x square plus x plus 1. So similarly you can able to see on the, okay, that is your table with a row and column. Now we are going to perform an, okay, addition and multiplication over this particular field. So we are going to generate the particular field with the help of your irreducible polynomial. We have x cube plus x plus 1, that is the polynomial we are going to use. So how we are going to perform addition and multiplication with respect to polynomial? Already we know that in the case of addition of two polynomials, we perform a XOR operation, right? You can able to see that here addition becomes XOR of these bits. So what is the XOR operation? We know when I am taking two inputs, if both the inputs are same, I will get 0 as output. If both the inputs are different, for example, I take 0 0, I will get 0, 1 1, I will get 0, 1 0 or 0 1, I will get 1. Similarly, if I go for multiplication, it is a shift XOR operation, shift and XOR operation. Remember that it is shift and XOR operation, or we say that AND operation, where it is going to perform with respect to your multiplication. And the important point we need to remember is the modulo reduction is done by repeatedly substituting highest power with the remainder of irreducible polynomial. When I am performing either an addition, generally in addition we do not have any higher degree problem. When I go for multiplication, normally when I am going to multiply two polynomials, for example x square into x square, what I will get? I will get x power 4. That is, again we can say that higher power if it's going to be higher power, then we have to perform a mod operation with respect to your irreducible polynomial to adjust the value to the particular field. So that is what we need to understand as the third point. So the first thing is we are going to consider zeros and ones can be represented as a polynomial as a bit string. Second, the two operations either addition and multiplication. Addition means XOR operation, and multiplication means shift and XOR operation. Whenever it is going beyond the higher degree, then highest power with a remainder will be going to be get with the help of your irreducible polynomial. So the previous table, from the previous table, now we are able to understand how we got the answer for these tables. Let us take addition. Okay, so for example, in this case it is given, we are taken the x square plus 1, that is 101 and 111, that example we are taken. So let us take addition operation with respect to 101 and 111. What we are getting, we can able to see that. So we are getting x plus 1. So we will see that with respect to addition what is happening. So we say here addition x square plus 1 plus x square plus x plus 1 is equal to x, right. So x square, then we are getting x. How we are getting x? So as the thing, we can take 101 XOR of 111. So 101 XOR of 111, when both the inputs are same, we will get 0 as the output. Look at from the MSB, most significant bit, 1 it results with 0, 1 results with 1, 1 results with 0. So as we know, 0, 1, 0 is equal to x. Similarly in the table also, we can able to see that, right, this value. So 101 plus 111, what I am getting is x. This is for addition operation. Similarly go for multiplication, when I am taking x plus 1 into x square plus 1. So how they do the polynomial multiplication? We will take the term, first term x will multiply with this, and 1 will multiply with this. What you are going to get is x cube plus x square plus 1, that is x square plus x cube plus x plus 1. Now we have to look to the value. You can see that it is going to be 1, 1, 1, 1. Even do just a XOR operation, shift with an XOR operation with a multiplication, where you get 1, 1, 1, that is higher degree. So when your value is exceeding that particular higher degree, then we have to go for reducing. The reduction is going to be done with the help of a modulo of irreducible polynomial, that is x cube plus x plus 1. So as you are going to do the modulo operation with a irreducible polynomial, we will take that x cube plus x plus 1 plus x plus 1, sorry, x plus 1, x cube plus x square plus x plus 1 mod x cube x plus 1 is equal to 1 x cube plus, that is plus x square is equal to x square. So the mod operation with respect to the binary digits, all 4 mod 1011 is equal to, that is what you are going to do an XOR operation, we get 0, 1, 0, 0. So this coefficient is 1, then we can say the term is x square. So what is our answer? We are getting x square. How we got this x square? Actually we got the answer as, that is x cube plus x square plus x plus 1, but this is a higher degree where we need to go for reduction with the help of irreducible polynomial given in the table. So for GF of 2 power 3, so with the help of that we can able to reduce the value, then after reduction what you are getting the answer is x square. So let us check this in the table. As what you can say, what is the value? We are taken two values, one is x plus 1, another one is x square plus 1. So what you need to get answer? X square. Just check with a particular table. So we can able to see that we are getting x is square. So that is what we can able to understand with the help of whenever you are going to perform a polynomial operation, where we need to understand how the multiplication and the additions are going to be taken. Next, what we are going to discuss is modular exponentiation. So whenever you are going to study about asymmetric cryptography, let us take an example of an algorithm called RSA. That is, when I am going to perform an encryption or decryption, always I will do with the help of the higher, okay, that is your exponentiation, that is modular exponentiation operation. So in order to implement an exponentiation related to some modular need to be done a lot. So always, so what we have to do is you have to perform an operation better to be doable and fast. Suppose let us take an example here, 2853 power 3397 mod 4559. So how we are going to perform a exponentiation operation so that we can able to get the result. That is where you can able to understand with the help of modular exponentiation. So whenever you are going to take an encryption process in the case of your RSA algorithm, we perform a high digits exponentiation, modular exponentiation. So we need to understand how to solve much faster and also much quicker in such a way that your algorithm able to encrypt the plain text to a ciphertext, similarly from the ciphertext to the plain text. Now we can able to see that now if I am taking this exponentiation, the approximately it is going to be 3397.4 in digits are going to be there, which is very difficult for a computer to perform. So by taking mod after each multiplication, that is going to be make very easier. So let us see that how we can able to solve the modular exponentiation value. With a simple example, let us take 23 power 3 mod 30. I want to compute the modulo value for 23 power 3. That is congruent to minus 7 power 3 mod 30. So how we are saying minus 7 power 3 is 23 is okay, where we can able to say that value with respect to minus 7, because 23 when I am taking 23 minus 30, what I will get? I will get minus 7. So minus 7 power 3 mod 30. So minus 7 square into minus 7 mod 3, that is power 3 we are going to okay, taking in terms of your square and minus 7. Now 7 square is 49, 49 minus 7 mod 30. So 49 is actually we get 49 mod 30, the remainder is 19. So we will get 19 into minus 7 mod 30, that is minus 133, that is congruent to 17 mod 30. So what is the final answer? Either you can directly take 23 into 23 into 23 mod 30, or we will take the 30 okay, 23 minus 30, that is minus 7, the after subtracting from 23, what is the minus 7 we will get, that power we can able to simplify. So therefore 23 power 3 mod 30 is equal to 17. So what if I had to figure out 23 power 16 mod 30? Again it is going to be very complicated, where need to do a multiplying 15 times. Is there any better way? So because 3, okay, let us, we can able to do it with a calculator. If it is going to be power 16, then we need to multiply 15 times. Okay, so how we can able to make it simplified? So there is one method, we say that is a fast modular exponentiation, or we can say that square and multiply. So square and multiply, the way you can able to understand that particular power is 16. 16 is multiple of 2. Let us take 2 into 2 into 2. We say that we will say 16 equal to 16. So how we are going to represent 23 is with the power to 2 into 2 into 2 into 2. So we say that 23 square 3 that square and square square. So all the time we are going to square it, we will get the value of 23 power 16. So instead of doing this for 23, we can also take it minus 7 as the previous case, we can able to solve it, because minus 7 square we able to fastly we can able to do it. So that is equal to 49 square, and 49 square is going to be, we take that, this is going to be minus 11, and square is going to be 121, this congruent to 1 square, and this 1 square is equal to congruent to 1, then finally we can say that 23 power 16 mod 30 is equal to 1, and same way it is able to do it with the help of 25. The previous method is repeated squaring, works for any exponentiation that is power of 2, right. We can able to do it with the help of power of 2. What is the thing if it is going to be not a multiple of 2? For example, this case we take 16, it is going to be multiple of 2, we can do it. But what about 23 power 25 mod 30? So in this case it is not a multiple of 2, that is where we have to go for breaking down into the sum of such a power. For example, 25 can be given as 16 plus 8 plus 1. So 16 is multiple of 2, 8 is multiple of 2, 1 is the what is to represent that 16 plus 8 is 24 plus 1 is 25. So applying repeated squaring to each part, multiply the result together, so finally we can able to get the particular answer. For example, here you can take that 20 power 16 plus 8 plus 1, we will be able to get the particular answer. So you can able to see that 23 power 16, 23 power 8, 23 power 1. So 16 we already know 1, 8 okay, it's going to be 1, then finally 23. So 23 mod 23 power 25 mod 30 is equal to 23. So what is the understanding we can able to from the first multiplication is, if it's going to be a multiple of 2, we can able to square and able to find out. As we have the value which is 25, this case where you are going to take it with the help of the power, already we know 16, and also we have find out for the 8. So 8 is also 1, that is 2 power 23 power 8 is also 1, 20 power 16 also 1. So 8 plus 16 will get 24, and finally 1, that is 23. So the answer what we are able to get from this particular step is 23 power 25 mod 30 is equal to 23. So where we able to do it much faster with the help of your modular high degree exponentiation. So here the decomposition is very important. How we are going to take the 25 into account so that you can able to. So from the binary, okay, so how could you figure out the decomposition? 25 plus is equal to 16 plus 8 plus 1 from the binary representation of 25. So how we are able to do, how I am did in the previous, how I make it as 16 plus 8 plus 1, okay, that we can able to do it with the help of the binary representation. So 25 is represented in binary value as 11001. That means this is 2 power 0, this is 2 power 1, 2 power 2, 2 power 3, 2 power 4. 2 power 4 is 16, that is 1 into 16 plus 1 into 8, whereas 0 into 4, 0 into 2, and what you have is 1 into 1. So now we can able to say that it is easier for any number, not only 25, if any number is given, how we can able to find to make it in the power of 2 is, first thing is we need to make the number in binary and represent with respect to their power. So can we tell which power of 2 appears where it is going to be 1 in the particular bit, if the power is not going to appear if there is a 0. So with the help of this, you can able to decompose any number and we can able to simplify the computation. And we also know about the property of modular arithmetic, where you can say that a mod n plus b mod n is equal to, we can say that a plus b mod n. This we already discussed in the case of your previous. Similarly have subtraction, similarly have multiplication. So this is what an example what we discussed related with our property. Let us take, if I take 11 mod 8 is 3, 15 mod 8 is 7. So what I can do is, suppose I am going to add 11 mod 8 plus 15 mod 8, I can do directly 3 plus 7, because we already know that 11 mod 8 is 3, 15 mod 8 is 7. So we can say that 10 mod 8 is 2. Similarly for subtraction, minus 4 mod 8, that is 8 minus 4 will get 4. That is because it's an additive inverse, so we take the mod minus 4. And multiplication, 3 into 7, 21, 21 mod 8 is 5, and 11 into 11 we can check, verify what is going to be happening. If it is going to be 21, we can verify similarly with the 11 into 15 also going to give the same answer. So exponentiation is done by repeated multiplication as ordinary arithmetic. So to find 11 power 7 mod 13, do the following. We take squaring and we will able to get the particular answer. So 11 power 7 mod 13 is 2 mod 13. So this is the sage algorithm to say that how to compute x power n mod m, right. So the function is given is an expression x as your value, exponent value is n, m is a modular value, that is modulus, where you take initial value y is equal to 1 and u is equal to x mod m. While n is greater than 1, we check whether we are getting the mod is 1. If it is 1, we will perform multiplication mod, and otherwise you go for taking the floor value, whatever you are going to perform mod, then finally you will get the output y, that is your result. So a good thing about modular arithmetic is that the number you are working with will be kept relatively small. At each stage of algorithm, mod function should be applied. So we can able to apply the mod function stage by stage to make the value very small. That is what it is saying, relatively small. For example, if I take 39 into 15 mod 11, we first takes mod to get 39 mod 11. So 39 mod 11 will get 6 and mod 11 is 4. Multiplying these two will get 24. We can able to finally get the answer as 2. And similarly we can also do with a modular division, but division it's going to be somewhat different. We call that as a inverse. For example, 5 divides 3 mod 11. So we say that 5 multiplied by inverse of 3 mod 11. That means your answer, when I am going to multiply, I should get 1. Already we have discussed in the case of your algebraic structure, where you have one property called inverse. Whenever I am going to perform any operation, I should get the identity element. Then I can say that a number is going to be inverse of other. So what is the inverse of 3 is, that is divide 3 mod 11 means, I can say that inverse of, okay, that means 4 into 3 is 12. So I will take 4 into 5, that is 4 into 5, 4 into 5 20 mod 11, I will take 9 mod 11, the answer is going to be 9. So what is the idea here is, what is the value of 5 divided 3, that is mod 11 is, we can say that 9 mod 11. So this you can able to do it with the help of your extended Euclidean algorithm. Already we know about Euclidean algorithm. Euclidean algorithm going to compute for GCD of two numbers. We already worked with this particular example. A and B is given. I want to find out the GCD, that is the greatest common divisor of A and B. So for that I am checking whether this is going to be the second B is going to be 0, then I return A as the GCD. But in this case, if it is not, is going for a recursive operation. When I am going for finding the inverse, right, here in this case, for smaller number it is easier for you to find the inverse. If it is going to be a very large integer, then it is going to be difficult for you to find that. So in order to solve it, we have an Euclidean algorithm. The number that has inverse in Z are relatively prime to n. So we can use an extended algorithm, see if x is a relatively prime to n, then we can know that an inverse does exist. So before going to proceed with finding of inverse, what you have to do is, we have to know that whether the given x is relatively prime to n. What do you mean by relatively prime to n is, when I am applying GCD of x comma n, it must give equal to 1. That answer must be 1. That is GCD of x comma n is 1. Then only I can able to find the inverse. So I say that when it is GCD is going to be 1, then there is a inverse exists. How can we find inverse without looking at all the remainder? So again it is going to be a large problem for when the value is going to be a large integer, as I mentioned. So for that only we have an algorithm called an extended Euclidean algorithm. An extended Euclidean algorithm where we can able to find any particular integer, what is the inverse of that particular number. So formalizing the backward step, we get the following formula. So we have the two variables, okay, we say that okay, initialized with 0 and 1, y0 and y1 is equal to 1. So 0 and 1 are initialized, and each stage, for example I am going for computing a inverse of a particular integer, yi is equal to yi minus 2 minus, that is what is this example? For example, I want to find out 2, that is yi is equal to yi minus 2 minus yi minus 1 into qi minus 2, that is whenever you have an I greater than 1. Suppose for example, I want to write for y, I want to find out for y2 is equal to y0, that is I is equal to 2, y0 minus y1 into q0, that is the, okay, let us take this I is 2, so q0, that quotient what you obtain after the performing an equivalence algorithm. From the equivalence algorithm we will get that. So this related to the magic box method. So where you can able to with the help of this extended Euclidean algorithm we can able to find out. Only thing is we need to remember is there will be the Euclidean algorithm we know already, which is used to perform a GCD of a given number. Now we have a extending that algorithm in such a way that which can able to help you to find the inverse of that particular number. So that is what here y is given. The steps are explained. So extended Euclidean algorithm where you can take y is equal to 0, I is equal to 1. We can able to try for 13 mod 22. So 13 mod 22 where you can able to see that with the help of extended Euclidean algorithm y is equal to 0. Each and every stage we take the coefficient, performing the mod operation, we are getting 17 into 30, checking it is going to be 1. The answer is also going to be 1. So you can able to verify that. Last step you are going to 2 where you are going to get the 17. Here you are getting 17. So inverse is going to be 17 to 13, we will get the actual 1. So we understood the purpose of modular exponentiation, and also we express the inverse multiplication with the help of extending the Euclidean algorithm, and also we have discussed about some of the examples that is fast exponentiation, and also we have solved some of the examples with the help of your modular exponentiation and inverse multiplication. Thank you.